Hello, can you hear me? Testing, can you hear me? Okay, so I'm going to be learning about heaps again. Hold on. All right, so I'm going to be learning about heaps again. Last stream I was learning about topological sorts, and this stream I will be learning about shortest path problems. Also, my stream does randomly drop. It has like lag spike, so I might randomly freeze. I might randomly start lagging. Just a heads up. Anyways, so let's start with this topological sort. So over here it says they want to print all the vertices, but it has to be like this. J2 cannot be printed before J1. The vertices coming after should it be printed before the vertices that come before. So assume that we need to schedule a series of tasks such as classes or construction jobs. We cannot start one task until after its prerequisites are complete. We wish to organize the task into a linear order that allows us to complete them one at a time without violating any prerequisites. We can model the problem using DAG. I forgot what DAG meant. The graph is directed because one task is a prerequisite of another. The vertices have a direct relationship. It is acyclic because a cycle would indicate a conflicting series of prerequisites that could not be completed without violating at least one prerequisite. So what they're saying is that if you have a cycle like over here, this task would have a prerequisite of this task would have a prerequisite of this task, but this task has a prerequisite of this task, so we are stuck in a cycle. So the first condition is that the graph has to be acyclic. The process of laying out the vertices of a DAG in a linear order to meet the prerequisite rules is called a topological sort. Hold on, DAG. A graph with directed edges. Directed acyclic graph. That's what it means. Hold on a minute. Hold on a minute. All right, let's go back. So, an acceptable topological sort for this example is 1, 2, 3, 4, 5, 4, 5, 6, 7. Another acceptable sort is 1, 3, 1, 3, 2, 6, 4, 5, 7. Because all the nodes after are like in the later section. A topological sort may be found by performing the depth first search on the graph where a vertex is visited, no action is taken, and the recursion pops back to the vertex. Function post visit prints the vertex. All right. Queue-based solution, we can implement topological sort using a queue instead of a recursion as follows. First, visit all edges, counting the number of edges that lead to each vertex. All vertices with no prerequisites are placed on the queue. We then begin processing the queue. When vertex V is taken off the queue, it is printed and all neighbors of V have their counts decremented by 1. Place on the queue any neighbor whose count becomes 0. If the queue becomes empty without printing all of the vertices, then the graph contains a cycle. Applying the queue version of topological sort to the graph of figure 14.4.1 produces 1, 2, 3, 6, 4, 5, 7. So this function over here is being applied to this graph. That's what they're saying. And they get 1, 2, 3, 6, 4, 5, 7 as an output. Okay, so top sort PFS Q counting the count of nodes and list V. So we're initializing the count of all the vertices to 0. And then for all the nodes, visit the neighbor and increment their count. And list is equal to energy. Okay. So we're incrementing the count of the neighbors. Then node count V. V is equal to 0, Q in QV. Process all the. Okay, let me see what this does. Nodes array begins with a list of courses. These are of activity in some random order. Count array shows the number of incoming edges, which is the number of unresolved dependencies for that node. So we have. There is no nodes list. Nodes list count. Okay, count list I understand. Or node list. They mean this. Count V is 0. And list is G neighbors V. I think this nodes over here is like a property of graph G. So 2114. Count array shows the number of incoming edges, which is the number of unresolved dependencies. So 2114 has one incoming edge. 2506 has two incoming edges. To increment the count of all the what do you call all the neighbors, right? All the next neighbors, the two neighbors. There's two and there's from. All the neighbors is going to increment their count. Then if we count V is equal to 0, add it to the queue. Okay, let's see. Start. Okay, so after after this step, we end up with a count list that counts the number of incoming nodes, right? The number of the number of incoming arrows, the number of edges going into it. Then we end up with this count. Then we end up with this count. And if it's 0, then add to the queue. While queue dot length is while queue dot length. So if there's a node in the queue, dq print out, and then we go, and then for every neighbor we decrease a count because we are going to visit it. And then okay, if the count is then 0, then okay. So 2114 is now visited, so the count will decrement. And now that this is 0, it will enter the queue. And in the next loop, 2114 will dequeue. D in queue. Yeah, and then decrement the count. And then the next one is 2505, so decrement it. Since it's 0, you output it. Also, similarly, we have 2506 and we have 3114, decrement both of them. Mark these, update the number of incoming edges. And lastly, we have this. So they have a topological sort without any recursion. Short. Okay, shortest path problem. Sorry, I'm getting a lot of lag spikes, so that's why I'm pausing in between. On a roadmap, a road connecting two towns is typically labeled with its distance. We can model a road network as a directed graph whose edges are labeled with real numbers. These numbers represent the distance or other cost matrix, such as travel time between two vertices. These labels may be called weights, costs, or distances, depending on the application. Given such a graph, a typical problem is to find the total length of the shortest path between two specified vertices. It's not a trivial problem because the shortest path may not be along the edge. If any, connecting two vertices, but rather may be along a path involving two or more intermediate vertices. So, for example, figure 14.5.1, the cost of the path from A to B to D, A, B, D is 10, 5 is 15. The cost of the edge directly from A to D is 20. Cost of the path from A to C to B to D is 10. A to C, B, D, 10. Figure 14.5.1, and there is no path from E to B. We set DEB to infinity. Use the notation DAD is equal to 10 to indicate that the shortest path from A to D is 10. Use infinity. We define WAD is equal to 20 to be the weight of HAD. That is the weight of a direct connection from A to D. Because there is no edge from E to B, WEB is infinity. So D is used for shortest distance. W is used for the weight. Also, I'm getting a lot of lag spikes. I may have to stop this stream, but I will see. If it continues, I might stop. Anyways, so the weight from A to D is 20. The weight from A to C is 3. Do we do from A? Okay, the weight from E to B is infinity. Shortest distance A to D is 10, has the weight 10. The shortest weight, I mean, the shortest weight A to D has 10. So 3, 2, 5, okay. We now present an algorithm to solve the single source shortest path problem. Given a vertex S in graph G, find a shortest path from S to every other vertex in G. You might want only the shortest path between two vertices S and T. However, in the worst case, finding the shortest path from S to T requires us to find the shortest paths from S to every other vertex as well. So there is no better algorithm for finding the shortest path to a single vertex than finding the shortest path to all vertices. The algorithm described here will only compute the distance to every such vertex rather than recording the actual path. Recording the path requires only simple modifications to the algorithm. Computer networks provide an application for a single source shortest path problem. The goal is to find the cheapest way for one computer to broadcast a message to all other computers on the network. For unweighted graphs, the single source shortest path can be found using simple breadth first search. When weights are added, breadth first search will not give the correct answer. One approach to solving this problem when the edges have differing weights might be to process the vertices in a fixed order. Label the vertices 0 v0 to vn minus 1 with s is equal to v0. In processing vertex v1, we take the edge connecting v0 and v1. To process v2, we consider the shortest distance from v0 to v2. Compare that to the shortest distance from v0 to v1 to v2. When processing vertex vi, we consider the shortest path vertices v0 through vi minus 1 that have already been processed. Fortunately, the true shortest path to vi might go through vertex vj. Such a path will not be considered by this algorithm. However, the problem would not occur if we process the vertices in order of distance from S. Assume that we have processed in order of distance from S to the first I minus 1 vertices that are closest to S. Call this set of vertices S. We are now about to process the ith closest vertex, call it X. Shortest path from S to X must have its next to last vertex in S. Thus, shortest path S to X is for every U which is an element in S, dsu plus weight ux. In other words, the shortest path from S to X is the minimum over all paths that go from S to U. Then have an edge from U to X where U is some vertex in S. How do you pronounce this? Dijkstra's. Solution is usually referred to as Dijkstra's algorithm. It works by finding a distance estimate dx for all vertices x in V. The elements of D are initialized to the value infinite. Vertices are processed in order of distance from S. Whenever a vertex V is processed, dx is updated for every neighbor x of V. It is an implementation of for Dijkstra's algorithm. At the end, array D will contain the shortest distance values. Dijkstra. So all of them are initialized to infinity. ds is 0. Uh, Minimum vertex gd. dv is infinity. Set value v visited. Find the next closest vertex. How do we find the next closest vertex? If dv is infinity, return g neighbors. Yeah, I need to know what this does. Call Dijkstra's algorithm with a start vertex of A. So all of them is set to infinity. Says the start node, the distance is 0. And mark vertex with the smallest value is now A market. Processing edge AC, update the distance value of node C to 7. I don't know what this is doing. So 7 and mark C is visited, right? Update the distance value of E 9 and mark vertex with the smallest value is now C. Mark it. Update the distance value of node B. Distance value of node B from C, right? Yeah. And then F as well. Smallest one is D, mark it. Leave the distance value of node F unchanged. Add a E. Leave the distance value of node F unchanged. CF and then finally B. There are two reasonable solutions to the key issue of finding the unvisited vertex with the minimum distance value during each pass through the main for loop. First method is simply to scan through the list of the vertices, searching for the minimum value as follows. So minimum vertex GT, initialize V to any unvisited vertex. G dot get value I is not visited. Then V is equal to I and a break. If for every node not visited and di is smaller than dv, v is equal to I. Because the scan is done n times and because each edge requires a constant time update to d, total cost for this approach is theta v square plus e is equal to theta v square because e is an o v square. I don't understand this. Find the unvisited vertex with the smallest distance. So it just returns which one is unvisited. I don't understand this. Initialize V to any unvisited vertex. V is equal to I break. So any unvisited vertex. Okay, so it marks V as any unvisited vertex. That's what it does here. And then get value not visited, and di is less than dv. And d is the distance from the main S, right? D is inputted here. Okay, I think I understand. So if initially it's di, initially is infinity, right? Di. Initially it's infinity, so it will set the value to I. dv. Does dv get updated? I don't think so, right? dv would be infinity. ts is 0. Minimum vertex. But this d array would have infinity for all of its value except for s. So it's not clear to me. D doesn't get a chance to get updated, so it's never going to be. So di would never be less than anything. It will always be infinity, right? An alternative approach is to store unprocessed vertices in a min heap ordered by their distance from the processed vertices. The next closest vertex can be found in the heap in theta log v time. Every time you modify dx, we could reorder x on the heap by deleting or reinserting it. This is an example of a priority queue with priority update. Implement 2 priority updating. We would need to store with each vertex its position within the heap so that we can remove its old distances whenever it is updated by processing new edges. Simpler approach is to add the new always smaller distance value for a given vertex as a new record in the heap. Smallest value for a given vertex currently in the heap will be found first. And greater distance values found later will be ignored because the vertex will already be marked as visited. The only disadvantage to repeatedly inserting distance values in this way is that it will raise the number of elements in the heap theta v to theta e in the worst case, but in practice this only adds a slight increase to the depth of the heap. Time complexity is theta v plus e log e, because for each edge that we process, we must reorder the heap. Use kv pair class, store key value pairs on the heap, with the edge weight as the key and the target vertex as the value. Here is the implementation for Dijkstra's algorithm using a heap. They said with each weight as a key, the target vertex as the value. It's possible to have for a heap to have the same key, right? Using minimum vertex to scan the vertex list for the minimum value is more efficient when the graph is dense. That is when E approaches V squared. Using a heap is more efficient when the graph is sparse because its cost is theta V plus E log E. However, when the graph is dense, this cost can become as great as theta V squared log E, which is equal to theta V squared log V. Now you can practice using Dijkstra's algorithm. Reproduce the behavior of Dijkstra's algorithm for a graph given for the given graph below. Click on the edges in the order they are traversed by the algorithm. Start with node A. In case of similar costs, add nodes alphabetically. Start node A. So what? Click on 4. Then we click on 4 over here. We check 5, 6, 7, and then 4, 4. The minimal cost spanning trees. The minimum cost spanning trees problem takes as input a connected undirected graph G, where each edge has a distance or a weight measure attached. The minimum cost spanning tree is the graph containing the vertices of G along with the subset of G's edges that one has the minimum total cost as measured by summing the values for all edges in the subset, and 2 keeps the vertices connected. Applications where a solution to this problem is useful include soldering the shortest set of wires needed to connect a set of terminals on a circuit board, and connecting a set of cities by telephone lines in such a way as to require the least amount of cable. The minimal cost spanning tree contains no cycles. If a proposed minimum cost spanning tree did have a cycle, a cheaper MCST could be had by removing any one of the edges on the cycle. Thus, MCST is a free tree with V minus 1 edges. It's connected undirected graph. But they have a weight. But if you want to remove a cycle, which edge do we remove? The name minimum cost spanning tree comes from the fact that the required set of edges forms a tree, spans the vertices, and it has a minimum cost. It has a minimum cost. So with subset of G's edges that has a minimum total cost as measured by summing the values for all edges in the subset. Gives the vertices connected. So 7, 1, 2, 5, 1. So this tree, this red tree gives the minimum sum, right, of all the edges. If C is not connected to D, instead D is connected to F, then instead of 1, we would have 2. The first of our 2 algorithms for finding minimum cost spanning trees is commonly referred to as Prim's algorithm. Prim's algorithm is very simple, starting with any vertex n in the graph, setting the minimum cost spanning tree to be n initially. Pick the least cost edge connected to n. This cost connects n to another vertex. Call this m, and this vertex m an edge and m to the MCST. Next, picks the least cost edge coming from either n or m to any other vertex in the graph. Add this edge and the new vertex it reaches to the MCST. This process continues at each step, expanding the MCST by selecting the least cost edge from a vertex currently in the MCST to the vertex not currently in the MCST. Prim's algorithm is quite similar to Dijkstra's algorithm. for finding the single source shortest path. Primary distance is that we are seeking not the next closest vertex to the start vertex, rather than the next closest vertex to any vertex currently in the MCST. Thus, we replace this line with this. Morning code shows an implementation for Prim's algorithm that searches the distance matrix for the next closest vertex. For each vertex I, when I is processed by Prim's algorithm, an edge going to I is added to MCST that we are building. Array VI stores the previously visited vertex that is closest to vertex I. This information lets us know which edge goes into the MCST when vertex I is processed. The implementation above also contains calls to add edge to MST to indicate which edges are actually added to the MCST. I need to see an example. We will call Prim's algorithm with the start vertex of A. Any vertex would do to start. Okay, let's say they do A and A and right now it's 0. And my vertex with the smallest value is now A, mark it and add it to the MST. Why are they calling it MST? Process edge AC, update the distance value. It becomes 7. Process AE, we get 9. Unmarked vertex with smallest value in is now C. Mark it and add it to the MST. Add edge AC to MST. Update the distance value of node B. Node B has distance value 5. And similarly for D, we have 1. Then F, we have 2. Unmarked vertex with the smallest value is now D. I see, I see. The unmarked value with the smallest value is now D. Mark it and add it to the MSD. And now in terms of D, we are looking at C and F, right? So F, this is 2, but F already has 2. So it shouldn't make a difference, right? But if we do this 2 instead of this 2, would it make a difference? FE, processing edge FB. Leave the distance value of node B unchanged. Then we have 1 and then we have B. Alternatively, we can implement Prim's algorithm using a priority queue to find the next closest vertex as shown next. As with priority queue version of Dijkstra's algorithm, a heap stores Dijkstra's element objects. We have key value pair. I think I will read this later. Prim's algorithm is an example of a greedy algorithm. At each step in the for loop, we select the least cost edge that connects some marked vertex into some unmarked vertex. The algorithm does not check that MCST really should include this least cost edge. This leads to an important question. Does Prim's algorithm work correctly? Clearly, it generates a spanning tree. because each pass through the for loop adds one edge and one unmarked vertex to the spanning tree until all vertices have been added. But does this tree have minimum cost? Proved by contradiction, let GVE be the graph for which Prim's algorithm does not generate MCST. Find an ordering on the vertices according to the order in which they were added by Prim's algorithm to the MCST. V0 to Vn minus 1. Let edge EI connect Vx Vi for some x less than I and I less than or equal to 1. Let Ej be the lowest numbered first edge added by Prim's algorithm such that the set of edges selected so far cannot be extended to form MCST for G. In other words, Ej is the first edge where Prim's algorithm went wrong. Let T be the true MCST. Call Vp where P is less than J, the vertex connected by edge Ej. That is, Ej is equal to Vp Vj. Because T is a tree, there exists some path in T connecting Vp Vj. It must be some edge E apostrophe in this path connecting vertices Vu and Vw, such as U is less than J and W is more than or equal to J. Because Ej is not the part of T, adding edge Ej to T forms a cycle. Edge E apostrophe must be lower cost than Ej because Prim's algorithm did not generate an MCST. This situation is illustrated in figure 16.5.2. However, Prim's algorithm would have selected the least cost edge available, would have selected E apostrophe, not Ej. Thus, it is a contradiction that Prim's algorithm would have selected the wrong edge, and thus Prim's algorithm must be correct. Okay, I need some time understanding this. Reproduce the behavior of Prim's algorithm for a given graph below. So first is this one, and then 3, 3 over here. Next we go to B, is 9 over here. Or it takes this, right? The least one. But why 5 and not 8? It selects 8 first and then replaces it with this edge later. So that was what I was guessing. Because over here, we start with A unmarked, then C becomes 7, and then we go to C, right? C1, 2. See, over here, E is set to 9, 7, 2, 1. What if this was set to 10? So they start with A, processing node, update the distance value. Distance value is 9. So then later when they process E again, hold on, where is that E? Process FE. So initially E is 9, but then when they process E again, it becomes 1. Leave the distance value of P unchanged. Because was current value is 5. So E they switched it to 1. Okay. These algorithms are quite hard to understand. Our next MCSD algorithm is commonly referred to as Kruskal's algorithm. Kruskal's algorithm is also a simple greedy algorithm. First, partition the set of vertices into V disjoint sets, each consisting of one vertex. Then process the edges in order of weight. An edge is added to the MCST and two disjoint sets combined. If the edge connects to vertices in different disjoint sets, this process is repeated until only one disjoint set remains. There's a process EF over here. They're breaking vertices into V disjoint sets, each consisting of one vertex, and process the edges in order of weight. Okay, so they start with this one over here. EF and EF. Why is there O? F connects to E, so E is in position 4. Then next they process CD, right? Because CD is 1. Then process the edges in order of weight, and edge is added to the MCST. Two disjoint sets combined. The edges, if the edge connects two vertices in different disjoint sets. C and D. 2. Okay. Then the next one is DF. DF. D. Parent of node D is C. Parent of node F is E. Union nodes. And then CF. Parent of C is C. Parent of F is C. They're already in union. CB, parent of C is C. Parent of B is B. Union them. Parent of F is C. Parent of B is C. They're already in here. AC. All right, we add A.